Well, let's go ahead and get started. My name is David Brown, and today I'm going to be giving a presentation that I've called TLS is Hard, or Why It's Hard. Little background, this started as a kind of a paper I wrote a while ago as we started discovering all of the things that we do wrong when we use TLS in these embedded devices. So to start with, I'll read this, you're not supposed to, but it says the Internet of Things, or IoT, is a system of interrelated computing devices, mechanical and digital machines, object, animals, or people that are provided with unique identifiers and the ability to transfer data over a network without requiring human-to-human or human-to-computer interaction. It's not really the best definition, it's kind of broad. Internet of Animals is kind of an interesting feature, but the thing to really take away from this is the Internet of Things is about things that are connected that aren't normal computers. They're not the computers you're sitting at or that kind of thing. So I found these lovely 3D models of some things that aren't humans and aren't animals, and we put these on the internet. And that's basically what IoT is. But that opens up all kinds of things for nefarious purposes with my little play school criminal. So we'll get back to these in a minute. So if you go to Google and you type in IoT hacks, you get 1.8 million pages of results just from that phrase alone. And the first one I found at the time I did the search was this thing that said 5 worst examples of IoT hacking and vulnerabilities recorded. And go to the link, it's still the first one last I checked. The examples that they give is this thing called a Mirai botnet, some hackable cardiac devices, which is scary. There was a baby monitor with vulnerabilities. There's a webcam. And then the Jeep Cherokee hack, which is a good read. They were able to, over the public cellular internet, over the network, basically get complete control over the vehicle, steering and brakes, just over the public internet, thanks to IoT and some vulnerabilities. So you keep searching. There's fun ones with titles like, what did I call it? It's the 7 most exciting or something like that. Sorry about that. The presenter notes don't show up here. It's the 7 craziest IoT hacks. And the thing about this, these are all real devices. These are things that you buy, that people have at home. And they're all real attacks, and something bad happens from that, whether spying from a privacy concern of a baby monitor to controlling the brakes of your car as you drive down the road. So recently, there was a Usenet security symposium. James Micken gave the keynote, and this was a thing that really stood out to me that he said. And I'll get into why I don't completely agree with him on this. But his point isn't that we don't care about security for IoT. It's that to him, it's not interesting because there's nothing different about it. We have devices that are connected to a network. We should do gateways and firewalls and all the kinds of things that we would do with a desktop computer to make it secure. We should do that with the Internet of Things. The other thing he said, though, is interesting. He's like, TLS is the only good thing we have. And I do agree with this. But where I kind of disagree with this is that TLS gets kind of hard on some of these small devices. When people think of IoT in a lot of contexts, they think of this. Something with a Raspberry Pi, runs Linux. This is kind of like a desktop computer, though. It's probably running OpenSSL. So when you go buy, that did work, cool. The thing's got gigabytes of memory in it. There's gigabytes of flash storage. You've got a CPU that runs in the gigahertz. And if you want to secure this, you link against OpenSSL. You just do it like you would on a desktop machine. So there's a lot of these IoT devices that are just like this. So think of the refrigerator. It'll have something that's powerful. We have mains power right there. There's plenty of space for a computer. Some of these refrigerators have, 19-inch monitors embedded in them too. And although this is interesting, and I do think the security is important for these, it's not the subject of my talk. Another example, kind of the other extreme, think of a light bulb. In this case, we actually do have power provided, but we want to be really small and really cheap. And these things usually have memory in the terms of like tens of kilobytes and maybe hundreds of kilobytes of flash and a CPU that runs at maybe 10 megahertz. And the thing is, we can't even really do TLS on these things. And they don't generally connect to the internet. There's usually a smartphone, a gateway, something like that, that they talk through some lower level protocol, and then that gateway will use TLS to talk to the cloud to send data. So what I care about are the toasters. And I picked this because it is the silliest thing I could think of that is a real IoT device. I didn't find the picture to put in there, but there is somebody who makes an internet-enabled toaster. And I don't know why, but we're in the middle ground here. We've got maybe hundreds of kilobytes of memory, maybe a megabyte of flash, maybe 100 megahertz CPU or 32 megahertz, something like that. But overall, these devices, they're interesting enough, they're powerful enough to do TLS. I mean, there's no theoretical reason, but it's hard because they're so constrained. That when you talk about, something is 60 kilobytes, that's a lot of space. It's not just a little file you store somewhere. So as we get into that, how does TLS? And I'm glad this got past the review, because I'm not young enough to actually say this, but this is kind of a thing people say. So if you think about a non-secure network, you have a bunch of layers. Those are defined by OSI or different people, but they're real. In this particular case, I have an IoT device on the left and a Linux kernel on the right. The only difference is the green box for kernel mode. So in an IoT device, you may not have protection between user space and kernel space, or you may have protection, but the layers are different, the boundaries are different, but the effect is the same. You have some application, you have some kind of HTTP library that goes to TCP, IP, some kind of hardware, physical interface, talks over a nice black tube, which is the internet, which is a series of tubes, and the applications talk to each other, but everybody can see what's going on. Oh, cool. So to add TLS, we just drop it in. It sits, importantly, between the application up here and the network stack. So some of the layers here, this would be called the transport layer. This would be described as the presentation layer. And then you have the application and other things that sit on top of that. And nobody actually uses these terms, and it, in fact, was originally called OpenSSL, the secure socket layer. And it's not even, that's not really where it goes, but we'll get there, why it's called that and all of that stuff. So what happens when you do TLS? If you just pull up Wireshark and watch it, all this stuff that happens here is in plain text and you can just see it. And the other interesting thing is I went out on the internet and searched for this, and I found dozens and dozens of diagrams that are wrong. It was really interesting to see that. And I'm sure there's something wrong with this one too. But this is based on a packet capture of me typing OpenSSL client connecting to a server. Starts with a client hello. We send a bunch of random data and a list of cipher suites. The server comes back with its own random number, the cipher suite that it likes from that list, a certificate, which is a chain of certificates, some key exchange information, and the message that says, I'm done with the hello. The client does what it needs to send for a key exchange. This change cipher message comes across, which is what says we are ready to be encrypted. And then it does a handshake message. It's encrypted. The server does the same thing. And at this point, all your traffic is encrypted and protected by whatever we agreed upon here. And that's where it gets a little complicated. Let's see if I can pull up the same diagram. No. There we are. So there's a bunch of stuff going on here that's important to the security of the system. There's these random numbers. Most of the protocols that happen inside for security use random numbers to exchange information and to negotiate a key without a third party being able to see it. This certificate chain is how the server basically proves who it is. People kind of miss this. It was on a list of IoT exploits. It was the top one of IoT devices that didn't bother checking the certificate of the server. And it turns out there's actually no point in doing TLS if you don't do that. The hallway conversation I heard, the quote's on a slide, that somebody basically said, yeah, TLS without checking certificates is worse than not using TLS, because at least with not using TLS, you know it's not secure. The reason is because it's very easy to intercept this, be a man in the middle, and you have no idea who you're talking to. The other thing that's kind of subtle from this is this cipher suite. There's dozens at least of cipher suites, which is a combination of cryptographic algorithms, authentication, all the pieces that are needed to communicate securely, all bundled up into this ugly string, which turns into a 16-bit number. These have to agree upon that, and we periodically discover things, oh, that's got a weakness in it, we should stop using that. Which gets interesting with an IoT device, because if you have limited code space, you probably don't want to implement 70 different cipher suites in your application. If you implement one that's discovered to be weak, then the server stops allowing that one. This communication fails here because the server says, I don't have a cipher suite I'm willing to talk to you on. What this really means is that this is another reason it's important to allow updates in IoT devices. So this is kind of a summary of what I just said. I didn't realize that this was here. That there's the cipher suite agreement. There's the verification of the certificate, which is not optional. And I'll say that again. The cipher suite verification, or the certificate verification should not be optional. If you don't do it, don't bother. So what does this mean for the implementation? Memory is a big one. Excuse me. I mentioned before these devices maybe have tens of kilobytes of memory, maybe hundreds if we're lucky. TLS, there's a certificate chain that comes from the server. If you use RSA, that's pretty big. It's kind of kilobytes. There's all the stuff to do RSA that needs memory. And the TLS protocol itself basically mandates 16 kilobytes for its record size. And there's an extension that allows you to negotiate smaller record sizes that would be useful for something like this. Great idea. Nobody seems to really implement it. So we're kind of stuck with these big buffers. Time, and I'm going to pull that one up. Oh, that's what I mean by time. Actually, time. It's important the device have a notion of time. The certificates that come back have a validity period on them that says this is good, was issued on this date, and it expires at this point in time. This is not as critical as checking the certificate that it's actually valid and applies to the host you're asking for. But you are supposed to be checking time, and there's some other protocols like the way Google's cloud services do authentication. You actually have to know the time within 5 minutes to generate this token or it won't talk to you. This is actually a hard problem. We don't really have good solutions for secure time on these IoT devices. What kind of ends up happening is you make an NTP request and you get the time back, and hopefully that doesn't get spoofed as well as the certificates and who you're talking to. The last one is randomness. We mentioned this is needed for most of these protocols. And this is starting to happen more. I've noticed I think the first device I worked on with Light we wanted to use it for all this cryptographic stuff and it didn't have a random number source in it. And if you don't have an unpredictable source of randomness, somebody can intercept your communication. Somebody can later decode what you've communicated. And these are all these things are real exploits that have really happened. And I need to hurry, apparently. So what makes this all messy is that I don't know if you've ever used OpenSSL or any of the TLS libraries. They're messy. It starts out with this thing with fonts that are smaller than you're supposed to use in a presentation. And it doesn't matter because, these are just all the things you have to initialize. And if you get one of these wrong or leave it out, it'll probably work. And there'll be something wrong and it'll be insecure. Then you open up a socket, you set up this stuff to communicate between TLS and the underlying layer, and then you can start saying TLS read and TLS write, and your data is secure. Yay. So how do we do this in Zephyr? So one of the ideas is something like a stream abstraction. And this is kind of really common. If you go get Python libraries, pick a modern programming language, they will use some kind of stream abstraction, and you can ask for a regular socket, you can ask for a TLS socket with some stuff, and then you get this abstract stream that you can read and write from. What's nice is you get the same API for TLS and non-TLS. But the other thing is you could also stick this under the socket API, and it's not really the right place for it, but it can be done. This isn't done in Linux because of the kernel user space separation, and it's important to emphasize, really, it is not done in Linux. There is TLS support in the Linux kernel, but it's just for the actual encrypted transport of the data. It's not an implementation of TLS. And this also keeps the same API, but the layering is kind of wrong. We end up with having these little out-of-band things to verify certificates, and what we end up doing is like set sock opt, and oh, here's a certificate that's allowed, and here's my client certificate. So what are we doing in Zephyr? We're doing the second approach, of course. There's reasons for this. We didn't just decide, well, that one's layered wrong, let's do it. The biggest one is that we have hardware that's already set up this way, where TCP stack and TLS is already on another piece of hardware. And if we stick this under the socket interface, we now transparently can get TLS with that. The other reason is that abstractions are scary. And I wish I was joking about this, but when you mention streams and that kind of thing, people think of classes, and it sounds scary, in embedded systems, so we don't want to do that. I was actually told maybe we could do the stream approach, but make it not look like classes, and maybe that could get in. So this last one is a little confusing. The TLS API, Embed TLS, OpenSSL, they're all very similar. They were intended to be used the first way. As a library, you hook it into socket, send and receive, and then it does its thing. In order to do this under the socket API, we have to do a bunch of shenanigans. That sockets allow multiple threads. These libraries are not reentrant. You can't just lock because everything would just deadlock. So what you end up having to do is that each time somebody calls read or write, if it's available, good, we get our data. If it would block, we then go to sleep and we wait for data to come in, and then we wake everybody up and they can all go check if that made their operation available. The real reason behind this is that there's not a one-to-one correspondence between TLS read and the underlying socket read. That there's writes and reads of data. It's a wrapped protocol. So where are we now? This first point was a note to myself that I forgot to remove. The demo is actually going to be at the demo, at the table, we hope, of doing this. And there's a lot of network changes in flux happening in Zephyr that we're kind of having to work along with, but a lot of things then have to change to do this API, to do these kind of changes. And that's the grunt of what I have, and apparently all of my time. So I guess we have, oh, we have lots of time. Okay. I didn't have to go quite so fast. Any questions? Yeah. Oh. This way they end up on the recording.
What are you guys doing about certificate revocation protocols and stuff? Because frankly, a lot of that stuff is somewhat kind of broken and not up to date, but Google has their own way of doing it. There's
right.
Yet newer things coming along, and there's the traditional stuff. So what's the thought here?
Not much as far as thought goes. I think we're still at the state of, well, how do we even get the root cert list to verify it? So, yeah, that's an open problem that we need to address, because the protocols are complicated for this. They kind of assume that you're a browser on a desktop OS. When it comes to memory, when you go to Google's IoT service, and they have, oh, here's the root certs your device needs to have in it, and it's 60 kilobytes. It's much smaller than the full list of 200 kilobytes, but that's a lot for an IoT device. So for the demo, I took the one root cert that applies and stuck that in the device, but if they change who signs their certificate, it'll stop working. Yeah, so I guess the answer is, there's a lot more to do. Anyone else?
So, any suggestions what we should do about Zephyr situation? Like, we agreed there was a lot of discussion regarding the stream versus under sockets layer. Choices, we had 2 implementations. We achieved compromise and agreed on this on the socket. So,
Where do we go? What do we actually do?
What do we do? Like, should we accept and like follow that everything? Like, as far as I know, your demo is based on the opposite approach. Like,
yeah. So that right.
Should we keep like this faction, dissident faction in Zephyr, or should forget about it? Or
Realistically, what will probably happen is the demo will get pushed in as it is, not using the correct API. So it'll fit with all the rest of the samples that each do something their own way. And then we need to keep that up to date as the TLS support gets into the socket library. We've talked about that before, whether we handle the asynchronous aspect by a single thread that does polling. Currently, the demo does a single thread with polling, and it's actually worse because it wakes up every 250 milliseconds, which is not a great thing to do for a battery-powered device, and uses that for timeouts because there's a keep alive that's needed for the MQTT protocol. So,
yeah, but you see the current situation is that all the samples in Zephyr using embed TLS directly were removed. Like, we standardized on this new
right.
socket that's a copy.
Yeah, so maybe we do need to make this demo use the new thing, but we have to do it in such a way that it works. We can't be multi-threaded, which we're not. So we have to get there kind of gradually. And the other thing is there's a bunch of changes coming to the network stack that we just have to keep up with and keep all of that working. Does that kind of answer the?
Kind of
Kind of.
answers, yeah. Thank you.
Yeah.
So did you see the secure socket paper at Usenix Security?
I don't think I did. Which?
So it was one of the award papers was
Okay.
they proposed basically adding an SO secure option to socket, so it looks like what you're implementing now. So that was the proposal, and they implemented a shared library injection like scheme on Linux, so that
Okay. So they still did it in user space, though.
it was all done in user space. But anyway, that appeared to be well received as a way to simplify, and it hides all these problems you're talking about in terms of the behavior of TLS and reading and writing. So you just use a socket and it works. So
And you don't have to figure out how to initialize it and get it wrong.
that's right.
Like
That's
everybody
right.
does.
So it's an interesting paper. It's worth taking a look at since we're looking
Yeah.
at that in Zephyr. It was, I can send you the link, but it was at the Usenix Security Conference last month.
Where James Micken. And by the way,
What's that? Last month.
yeah. His presentation is pretty entertaining. His humor is interesting. You may not be able to get past that, but his kind of fatalistic depression about all of security comes through, but it's still a little bit practical. I think we're good on time. Any last questions? All right, well, thank you.